For many generations, people have wondered about the biggest questions regarding our existence, but we haven't had enough clear evidence to find the answers. What is our universe? Where did it come from? How did it get to be the way it is today? And what will its ultimate fate be? In the past, philosophers, poets, and theologians used to tackle these questions. However, things started to change in the 20th century when we gathered lots of scientific evidence from the universe itself. This evidence has led us to verifiable solutions, and today we can confidently state the answers to many aspects of these questions and more. But what does that mean for the journey from here to eternity? And how will the rest of our cosmic history unfold? Is it an expanding universe which won't collapse back later into a new Big Bang? What happens as time proceeds to infinity? Eventually, our galaxy is the only thing we can see. Do the stars die and drift in the dark? Does the central black hole eventually swallow everything? If so, does it eventually decay to nothing? There are many events that scientists can confidently predict will have our current understanding. Here's how it will happen as time marches forward. Based on will all come to an end. It all began some 13.8 billion years ago from a hot, dense, rapidly expanding state known as the Big Bang. That's the first moment in which we can describe our universe as being full of matter and radiation, and stepping forward from that state, given the known laws of physics, enables us to explain how the cosmos took its modern shape. Our observable universe is filled with approximately 2 trillion galaxies, occupying a region of space that we can access for about 46 billion light-years in all directions. After nearly 14 billion years of cosmic evolution, practically every galaxy is filled with tremendous amounts of heavy elements, capable of forming rocky planets, organic molecules, and the building blocks of life with each new star that forms. Our own Milky Way alone contains around 400 billion stars, and we're bound together in our local group of galaxies. In between groups and clusters of galaxies is the expanding fabric of empty space, dominated by dark energy, an energy inherent to space itself. Over time, however, everything that binds the universe together will decay away. At present, we have a high level of confidence in our understanding of the universe. While there are minor uncertainties, typically around a few percent, we can describe the universe as follows. It is expanding. This expansion is uniform in all directions. The rate of expansion is approximately 70 kilometers per second for each megaparsec of distance. The universe's energy is distributed among different components, such as dark energy, dark matter, normal matter, neutrinos, and photons. Our universe is also filled with different structures, such as planets, stars, galaxies, groups and clusters of galaxies, and cosmic filaments that create a web-like structure on even grander scales. Objects that have gathered sufficient matter and experienced significant gravitational attraction over extended periods have become stable, bound structures. These bound structures are no longer subject to the ongoing expansion of the universe. However, isolated bound structures that are not gravitationally connected to each other will continue to move apart over time as the universe expands further. The local group of galaxies, the M81 group, the Leo group, and the Virgo cluster are all impressive examples of nearby groups and clusters of galaxies that are all individually bound, but that continue to expand away from one another as the universe continues its expansion. This indicates that our local group, consisting of galaxies within approximately 4 to 5 million light-years of the Milky Way, will remain gravitationally connected as the universe continues to expand. However, galaxies located beyond the local group, although they may stay bound to their own galaxy groups or clusters, will not become part of our local group or establish gravitational ties with us. These distinct groups of bound galaxies can maintain their cohesion, but aside from galaxy groups and clusters that are already bound and merging, larger cosmic structures will disintegrate due to the influence of dark energy and the universe's accelerated expansion. Over a span of several billion years, we have a reasonable level of confidence in predicting both local and cosmic events. The sun will undergo changes, growing hotter, swelling, vaporizing Earth's oceans, and eventually becoming a red giant before reaching the end of its life. The local group will persist as a bound system, causing galaxies within it to attract and merge, leading to new star formation and the depletion of gas. 4 billion years from now, the Milky Way and Andromeda will merge, giving rise to a new galaxy referred to as Milkdromeda. In about 10 to 15 billion years from now, all the galaxies in our local group will undergo a gravitational encounter with Milkdromeda, leading to their absorption and assimilation into this larger galaxy. As these galaxies merge, the gas within them will create new generations of stars, but it will also be gradually exhausted. Consequently, the rate of star formation will decline. With insufficient fuel to generate new stars in significant numbers, old stars will outpace new star births, causing the overall population of stars in our galaxy to diminish. Meanwhile, the other groups of galaxies will continue to move away from our own. While the local group becomes more concentrated, this applies individually to the other groups and clusters. On larger cosmic scales, these groups will not only keep moving away from each other, but will do so at an increasingly rapid rate. This phenomenon is what scientists refer to as the accelerated expansion of the universe. Every individual galaxy not gravitationally bound to ours will appear to move away from us at an ever-accelerating pace over time. Eventually, all galaxies outside the local group will recede from us at speeds faster than the speed of light. With each passing moment, more stars and galaxies will become forever out of our reach. Surprisingly, a staggering 94% of galaxies within the observable universe are already in this category. But within our local group, the decline of stars, planets, and life will be very slow. After only a few billion years, all stars more massive than the Sun will burn out, leaving only the cooler, redder, lower mass but longer-lived stars behind. As the Sun-like stars die, they blow off their outer layers into planetary nebulae, which returns large quantities of hydrogen and helium gas back into the interstellar medium. As new gas begins to populate the galaxy, it will form molecular clouds that gravitationally grow. After enough time, those clouds will gravitationally contract, leading to a continuing trickle of star formation after all. Concurrently, interactions between stars and stellar remnants within the galaxy will occur. Over time, the more massive objects will be drawn toward the central region of Milkdromeda, while lighter ones will receive high-velocity kicks, propelling them toward the outskirts or even ejecting them from the galaxy entirely. This sequence of events will entail black holes gathering in the galactic center and eventually merge, collisions between stars and brown dwarfs, resulting in the formation of heavier stars, the galaxy developing a central concentration of stars and a diffuse halo, stellar systems losing their Oort clouds, Kuiper belts, and even planets due to close encounters with other stars. Even the smallest stars running out of fuel and perishing. The expulsion of many of the lightest stars from the galaxy altogether. The key question revolves around the frequency and rarity of these events and the timescales over which each process predominates. The smallest stars, still capable of igniting nuclear fusion in their cores, will endure the longest. Stars like Proxima Centauri will persist for trillions, not just billions of years. The most diminutive stars may shine for up to approximately 10 trillion years. When these stars deplete their core fuel, they will evolve into white dwarfs, a process similar to that of Sun-like stars. These white dwarfs will gradually lose heat and eventually cool to become black dwarfs, a transformation taking anywhere from 100 trillion to a quadrillion years. While the merger of supermassive black holes is expected to occur within a few billion years, resulting in a supermassive black hole several hundred million times the mass of the Sun at the center of Milkdromeda, other processes will unfold over much longer periods. Gravitational interactions among individual objects within the galaxy will become significant, with the outermost objects bound to stars being the first to be expelled. By the time most of the currently existing stars have faded away, many stellar systems will have lost their Oort clouds, Kuiper belts, and outer planets. For instance, in a quadrillion years, the solar system may consist solely of a black dwarf, orbited by remnants of Mars, Jupiter, and Saturn, along with any remaining moons. While it might be tempting to assume that the universe will become completely dark once the last remnants of stars have faded away, there's another source of illumination that will come to the forefront: the mergers of brown dwarfs and other celestial bodies known as failed stars within multi-star systems. We now have compelling evidence that all objects orbiting each other will eventually see their orbits decay, leading to spirals and mergers. When two brown dwarfs with a combined mass exceeding approximately 7.5% of the current mass of the Sun merge, they will give rise to a fully formed star, ushering in a new era of stellar birth. In fact, any planet orbiting one of these newly formed stars, if it possesses the right conditions for life, might have the chance to evolve into a living world once more. Even in a predominantly cold, dark, and seemingly empty universe, life may find a way to thrive again. The timescale for gravitational waves to trigger these mergers depends on the initial conditions under which multi-star systems formed. Nonetheless, many of them are likely to evolve into stars during the first approximately 100 quadrillion years of the universe's history. Similar to the previous low-mass stars, they will burn through their fuel for trillions of years, continuing to emit light for hundreds of trillions to a quadrillion years as white dwarfs before eventually fading into black dwarfs. Given system, there is approximately a 99% chance, if it doesn't evolve into a star during the initial 100 quadrillion years of cosmic history, that it will undergo a significant gravitational interaction leading to ejection. There's roughly a 1% likelihood of a collision occurring, whether between two stellar remnants or a brown dwarf and a stellar remnant, resulting in phenomena like nova, kilonova, or supernova. About 1 in 10,000 of these systems will be drawn into the galactic center, where a supermassive black hole will ultimately consume them. The typical timescale for ejection ranges from approximately 100 quadrillion to 1 quintillion years, while the timescale for random collisions falls within the range of 10 to 100 quintillion years. On the other hand, the timescale for being devoured by the central black hole is measured in sextillions of years or even longer. Consequently, most of the objects composed of regular matter within the galaxy will be ejected, while only a few will meet their fate in the belly of the central supermassive black hole. In the end, just a handful of remnants will remain within what's left of our galaxy, enshrouded by an immense halo of massive dark matter. The majority of planets and stars that ever came into existence will be expelled into the vastness of intergalactic space, where they will drift through the void for all eternity. However, there's another way in which bursts of light will continue to permeate the cosmos, through the evaporation of black holes. A black hole with the mass of the Sun will evaporate over the course of 10 to power 67 years, while the most massive ones, reaching tens of billions of times the mass of the Sun, will evaporate in a Google year, approximately 10 to power 100 years. This process, although the slowest among those we've discussed, occurs much faster than the timescales required for non-ejected masses to dissipate their orbital energy through gravitational waves. These supermassive black holes will begin to decay at a much swifter rate than they grow once several sextillion years have passed. Consequently, only these final blips from black hole evaporation will continue to illuminate the universe. Everything else will have become cold, lifeless, and degenerated by then. Nonetheless, there are certain unresolved questions that could introduce subtle variations to this narrative. Dark energy may not be a cosmological constant, but could evolve with time, leading to either a big crunch or a big rip, or something else entirely. Or maybe we may not be in the true vacuum state of the universe, and if we experience vacuum decay, so could our fate. Atoms that we presently think are stable could wind up decaying on long enough timescales, and perhaps, although we don't think it's the case, it's plausible that a gravitational interaction in a nearby galaxy group could lead to other members someday joining our local group. We can only extrapolate our future based on the limits of what's known today.